This is the 19th video on advanced J1939 for technicians. I'm connected to a machine and you can tell that there's definitely some problems with the CAN network on this machine. We have probably one or more controller that has an issue. And if I go ahead and pause and we'll zoom in and we'll take a look, we can see that I've got apparently some device that's transmitting here. All I can see is CAN high. I don't see anything for CAN low, and CAN low seems to be following CAN high. If I look at a device such as the engine controller here transmitting the engine speed message, I can see that even the CAN is so robust that we're still able to decode this. We have occasional error frames on the CAN bus, and we have maybe one or more devices that are not communicating. I may have DTCs for that device. Its message is not being present. We can definitely tell that we've got something electrically wrong with this CAN bus. Because we're looking at channel A minus B, which would be CAN high minus CAN low, we can see by the differential that's shown here in the white trace that we've got sufficient amplitude to be able to decode. So the other controllers that are on the CAN bus, they're able to decode this, and we can tell we've got an acknowledge bit that's out here. We've got other devices that are saying, yes, I recognize this, that these messages are correct. I've got, I don't know, 3 or 4 devices that are correctly communicating on this CAN bus. So all of the other devices are, for the most part, pretty satisfied with the amplitudes, the levels, the obvious bad waveforms that I have on this CAN bus. So, as I said, if we look at the device or devices that are communicating, I can see that I can't decode this. And if I were to go into the decoder, I have it set for A minus B. I could try dropping the thresholds way down. We could see we'll drop the hysteresis down to like nothing. And let's see if we're able to decode. And we can see that we still cannot decode these messages. I can decode the others. Some things that I might also try to do, I could change my decoding so that instead of looking at A minus B, we could just try it with channel A, and we'll see. And we can go ahead and set our baud to the 250K that we know it is. And once again, I really can't decode this. I don't know. It looks like there's some intelligence there, even though I'm looking at just channel A and I'm trying to decode based off of it. It's not able to detect any intelligence there. So if I look at this, I'd really like to know which controller this is. Of course, I could go around, I could try disconnecting each controllers, but if I had 20 or 30 that were located throughout a machine that might be really hard to get to, that could be a challenge. And to save time, it'd be great if I could know which device this was that had a problem. So one of the things I can try doing, I'm going to look at this waveform again. We'll look at it in a little more detail, and we'll try to figure out if we can decode this. So let's take a look at what we have for an amplitude of it. We have about the peak amplitude where this is somewhere around 3.8 volts. If I look at the lower threshold, it looks like it's somewhere around 2.95, so about 3, so about 800 millivolts. If I could just look in that range, that would be great. The other thing I need to do is I need to get this so that the logic levels are something that are near 0 volts and approximately something greater than 1 volt would be great. But let's see what we can do to change this. So instead of looking at A minus B, one of the things I can do is I can add a math channel. And I'm going to go ahead and create my own math channel. I actually have one here that I created before. It's called A minus 2.5. So what this is going to do is going to take whatever channel A is, and it's going to subtract 2.5 volts from this. You can create your own math channels. The instructions for how to do that are in the Picoscope software. It's pretty easy. So we'll go ahead and we're going to use this A minus 2.5. I'm going to go over here to the encoder, and I'm going to change it to A minus 2.5. And we said it looks like we've got about, let's go 800 millivolts. We'll drop the hysteresis down to like this. And let's take a look. And we need to get our baud rate set again because it couldn't recognize it. And let's see if we're able to decode based on this. And sure enough, there we go. I have a decoder that is now telling me that my problem is with source address EB. Now, what is source address EB? I happen to know from working on other machines that are like this. I might have to connect to it, get an inventory of the CAN bus and find out what it is. But if it's something I'm used to working on, this is actually a proprietary device that I know that is on this machine. It is something called a temperature, pressure, humidity sensor. And the problem that I apparently have with this is something wrong with the CAN low. And I happen to know that the problem is I disconnected CAN low from the device in order to create this waveform. You can see all the havoc that it's created on the CAN bus because it's not present. So if I know where source address EB is, I can go find source address EB. You can see pretty much nothing else is getting decoded using that criteria. This is one of these things you might have to just experiment with and play around with in order to get it to work. We can see by the waveform nobody is acknowledging this. We don't have an acknowledgement because nobody is interpreting this. All of the other controllers are using the criteria of CAN high minus CAN low, and it needs to be greater than a volt, for the dominant bit and near 0 volts for the recessive bit. So by creating my own math channel and then applying that math channel to the decoder, I'm able to resolve this. So this is a very useful feature, at least with the picoscope. I don't know if other manufacturers who have USB oscilloscopes, automotive oscilloscopes, this is possible, but it definitely is with the picoscope. So this is definitely one of the things that I like about this tool. Okay, I've now went to that device that was a smart sensor. I was able to go to it. I found that I had removed the CAN low terminal from the sensor so that it only had CAN high. And now we can see if I look at the waveform on this machine, everything's back to normal. I don't have any more error frames. I can see if I were to go find the device EB, let's take a look at it. If I zoomed in on one of its messages, we can see now that everything looks normal. This looks like it's back where it should be. You might have also noticed that we had very rapidly, this device, this EB, even though it doesn't transmit, source address FB is, no, it doesn't transmit very often, we noticed that it was really disrupting the CAN base. And the likely cause of that is, even though this only transmits maybe once or a couple of times per second, it was transmitting repeatedly because there was apparently no devices that were acknowledging its message. So it kept repeating this message, even though it was stepping on other traffic, if you would. The CAN transceivers and the rest of the bus were able to successfully decode the same way that we were with the oscilloscope, even though the problem was there. So this is as I said, it's a very powerful tool or diagnostic technique that you can use to help you narrow down where your problem may be on the CAN bus. So we'll take a look at another failure. I'll go ahead and introduce that. Okay, here I've created another failure, and you might recognize this from a previous video. In this case, what I have is we can see that there's apparently, we'll zoom in, we'll take a look at the acknowledge bit on all the messages. There is this pattern. Even though we have what appears to be something very strange, something causing a very CAN high and CAN low to both go to very different levels and a lot of oscillations and things, we can see when channel A or CAN high is subtracted from CAN low. So we look at the differential, we can see all the messages, for the most part, everything is still working. We can zoom in here on this one message, which is when you may recognize the problem. This is once again that temperature, pressure, humidity smart sensor. It's easy to get to. I added a couple of 100 ohms of resistance to the ground of this sensor. Because this is a really low power device, it really doesn't have anything that it drives like an output. Putting resistance on the ground of this sensor still permits it to operate as long as it's able to have sufficient voltage to do so. It does, however, as we've seen in other videos, it does cause an offset of that signal. We can see it really looks like a bunch of garbage, but when we decode it, we've got a pretty decent level. We can see here it's about 1.5 volts. Truthfully, this isn't causing any error frames on the CAN bus. And so since it isn't causing any error frames, it may be something that's intermittent. I might not even know if I have a problem until I put an oscilloscope on this, or that device may not be working correctly. And so once again, I can use the CAN activity to direct me to it. Here, once again, I can see that it is source address EB and hex. I know that from other machines that is that smart sensor. So if I look at why I have the acknowledge bit have this kind of a pattern, you can recall that all of the controllers on the CAN bus, if they recognize the message and they agree with the CRC, the redundancy, the cyclic redundancy check, that indeed they'll go ahead and put an acknowledgement on the bus. So we can see this pattern looks like this because that sensor is, just like everything else, driving the CAN high and the CAN low to the pull up and pull down values that are within the controller, like we've shown on other videos. So this is an instance where, once again, I can get to that device using what I can see on the scope patterns. I can see that I have what appears to be something really wrong. If I zoom in on that one problem waveform, and in this case, I didn't have to change my decoding. I might have to in some cases. I might have to do some of the tricks where I would go into the decoder and change even possibly this hysteresis or change this threshold. Okay, I've introduced another problem, and this one's a little harder to get to the root cause of. I'll go ahead and pause it and take a look at what we have for messages. So we can see here's that sensor with, so our voltage, where's our center of a voltage? Somewhere around 2.5, as we would expect. This is the smart sensor, the temperature, pressure, humidity sensor. If I zoom out though, and I look at most of the other messages here, so the engine controller, my center of the voltages is up around somewhere around 4.8 volts. I've got peak voltages on this, reference to ground of about 6 volts. And for CAN low, somewhere down to about 3.6 volts. So there's definitely some problem with the CAN bus here. We can see that I've got another message here from some other device. We'll zoom in on it and take a look at it. Once again, it's the engine controller. I can see that it's the same kind of thing, but it's really elevated. I've got CAN values where it's centered on about 7 volts. So there's definitely some issue with this machine. We can see a lot of this is engine messages. One thing to be cautious of, don't necessarily condemn the engine controller as being the problem, the ECM, because it is a device that typically transmits quite a few messages per second. So we've got about 50% bus utilization here, and probably more than half of that is going to be the ECU. So just probability, just statistics, the engine controller is going to be the device that's transmitting more than about everything else. So looking at this, as I said, I gotta figure out what's wrong. And unfortunately, the issue that I have here is, once again, it's a ground problem. But in this case, it's not a low powered device like the smart sensor. This is actually it is a NOx sensor, so it has it draws quite a bit more current. So I've added, or I've introduced some resistance to the ground of the NOx sensor. The NOx sensor uses source address 52 in hex, and as we can see here, we do not have a 52, so it is not communicating. I don't have anything where I can even look like I have if I go through some of my waveforms here, I don't have anything that even looks like data that wasn't decoded. So I'm pretty sure that I've got everything here. Everything that's on the CAN bus is communicating other than that NOx sensor. So in this case, I think what I would start with if I'm troubleshooting this, because this is such a strange pattern, I believe what's happening here, the device is finding, if you would, the NOx sensor is finding sufficient ground back through the CAN bus, through CAN low. It's finding, or through CAN low and CAN high, it's finding sufficient ground to be able to start to boot up and to try to turn on. And when it does, it drops its voltage at its terminal so low that it just stops communicating. So I think that's what we're seeing in these great big bursts. We just happen to hit the times when the knock sensor is trying to boot up, but it can't because it has a bad ground. So in this case, to troubleshoot this, instead of going around and disconnecting all of the controllers and looking for some problem, because this is obviously a problem, the thing I would probably do is look to see what messages I have for devices that are missing. So more than likely, the ECM in this case is going to have a DTC that indicates that the knock sensor is not present. It's not there on the CAN bus, one of the knock sensors. And from that, I would probably go first when I see something like this to that knock sensor, and I disconnect it from the CAN bus and see if that fixes my problem. I'll go ahead and do that, and we'll see what that does. So you can see the waveform looks a lot better. I'm centered around where I should be, somewhere around my 2.5 volts. I've disconnected the knock sensor. That was apparently my problem. So I'd need to troubleshoot the knock sensor. Hopefully the diagnostic procedures would have something about checking power and ground and load testing that power and ground was something that's going to draw similar current to what the knock sensor is going to pull. So in that case, I could have, I might have condemned the knock sensor as being the problem. It may or may not be. In this case, it just happened to be that I had resistance to ground of that device. So you can see, even though we had the same kind of failure, I had resistance to ground on a device. It really matters what the device, how much current it draws, if you would. And from device to device, you might find different results. And it may depend on even how much resistance it has. In this case, I had a couple hundred ohms of resistance on the knock sensor ground. That was enough to really change the waveform and to drive it way up as the knock sensor, basically, if you can imagine, its 12-volt power supply was partially shorting back into the CAN bus. And I've seen this before on a lot of devices, various devices. It really is hard to troubleshoot. And in this case, we could use the fact that we knew it was the knock sensor. We had a clue that it was a knock sensor because I had a DTC that said the knock sensor was missing. So we'll try, I'll change the resistance. I'll change this, I'll add it back in, but we'll put it to where it's not so much, and we'll see what the waveform looks like. We'll just add a couple of ohms of resistance. Okay, so this is the same machine. The only difference now between this and the last display is that I've reduced the resistance from a couple hundred ohms to about 10 ohms that is on the ground for the knock sensor. So if we can look at the data, we're getting some pretty strange patterns here. If I look at some of these messages, I can see that this is the transmission controller, and partway during the start of the transmission, we can see this, it's swooping up and it's swooping back down, which is really kind of strange. So if I look at where my voltage center is, here's my 2.5. I've got this increased up to like 4.3 now. And so my failure is the same thing as I had before. I have the knock sensor, which is going to be source address 52 in hex. I can see that it's communicating, but something about it doesn't look quite right. So if I were to look at any of the messages from the knock sensor, if I were to zoom in on them, I can see that unlike the other waveforms, it's got something about it that doesn't look right. I can see that it's not nice, clean drive to 2.5 volts. The other controllers that are on the bus, anytime we go to that recessive state where it should be driving both CAN high and CAN low to 2.5, this knock sensor is trying to drive it a little higher than that. It looks like it's going up to somewhere around 3.2, but the other devices are driving or pulling this back down closer to that 2.5. So that appears that what we have anywhere where we have the knock sensor that's communicating. So in this case, I would have a knock sensor more than likely with 10 ohms of resistance in it. It's enough for the electronics in the device to power up, but as soon as it would turn the heaters on or the heater on inside the knock sensor, which is going to draw a few amps, this is going to fall on its face. The device is probably going to reset. It'll come off and it would be on and off of the CAN bus, and I'd have some DTC related to missing knock sensor or even something about knock sensor invalid. So anyways, this is the same failure mode. You've seen it. It depends on the device and it depends on the amplitude of how much resistance I have in the ground, but it's the same kind of thing. I can use the I can use the scope and get to that source address and try to figure out, in this case, 52 hex, which is that inlet NOx sensor. I'm able to go to it, to troubleshoot it, check things like the power and ground on it first, make sure I don't have any resistance on my CAN circuits, and then be able to fix this machine and to fix this CAN bus, hopefully without having to replace any parts. In this case, just the fact that I added 10 ohms of resistance to the ground. So this is all for this episode. I'll probably do at least one more for this series and show some of the tools that are used by engineers to diagnose the CAN bus. I've had questions on that. I've got a lot of the tools that I've used over the years that have been very handy. So we'll probably do one final episode on that, and I think I'll be done with this series.